that's where we're going to go. So we are here at the Global Ocean Week, so nobody will claim here that the ocean plays an important role in our daily lives and the economic side and the climate. So, so I just want to make a point here that we will focus this joint presentation on the ocean's role within climate variability, and we will go from the global scale to the regional scale, from the global scale on heat storage, and going then on the example on the regional sea level changes. So I will make a point here on the energy balance in the climate system. So normally, if there is no external forcing, climate forcing, the amount of incoming energy is balanced by the amount of outgoing in fair variation. And if there is a climate forcing from outside, which can be due to natural climate variability, but also to human-induced changes, there is an imbalance between the incoming and outgoing amount of energy, and currently we measure a positive Earth energy imbalance where we have more energy coming into the system than the energy which is going out. So the majority of this energy is stored in the climate system. This energy is stored in the climate system, and the majority is stored in the oceans with 93%. So we had come together with a group of experts from the different components in estimating this energy transfer, and the fundamental message we gave out from this work was that the current Earth energy imbalance, it's mostly caused, and it's also the result of the IPCC, by human activity and how this is driving our global warming. But also there's that we were claiming that the absolute value of the Earth energy imbalance is the most fundamental measure of defining the state of global climate warming and how much energy is still in the pipeline and in the climate system. So there are different methods to determine this parameter. So there are 4 specific methods. The first one is the direct measurement from satellite observations at the top of the atmosphere. And then there is an inventory you can do from the surface of the Earth by the mean of the exchange of energy at the Earth's surface. You can go for the part where you have the storage of energy in the climate system. As said before, its majority is given by the estimate of the time derivative for ocean heat content, but also for the melting of sea ice and also of the warming of the land surfaces and the atmosphere. And you can have an estimate as derived from the climate model. So also this work had given a discussion for these different components, and we have shown that for the satellite observations are the most useful means to track the changes in the Earth energy imbalance, and it's the most precise one and can be used in order to understand the fingerprints of the changing in radiative forcings. The surface flux budget, the inventory of the surface flux budget is still a method which has large uncertainties, and there would be a way in order to improve this method by going through the regional budget constraints. We came to the conclusion that the ocean heat content is the best practical method in order to get an estimate for the absolute values of the Earth energy imbalance. And finally, to give a point on the climate models, which can provide greater insights into the underlying mechanisms of changes and in the energy flow through the climate system. So pointing here, I will come back then to the ocean heat content method. And that's what has been done recently for those estimates. There are different, I've just picked, it's not a whole inventory, but it's picking up the most recent analysis, and there are estimates for longer time periods which have showing lower values, and the most recent time series are going from going up to 0.5 to almost 1 watt per meter square. So there are different in those estimates, but all estimates show that there is a positive value in the climate system and leading to then responding to the accumulation of heat in the climate system. So the estimates of heat content had been done by several groups, and this is just an example which has been done by a community work in 2013, giving an intercomparison of these different methods from the different groups, showing that there are still large increases. So the main message was even if there are large discrepancies between the different methods, there's a positive increase, and we have warming in the global oceans, but still there's a need in order to understand where are those discrepancies coming from. So these discrepancies are, as you can see, at decadal timescales and at interannual timescales. So one point is first to go back to the source. So the source is the data set, and the data set can be distinguished between the period where we had historical measurements before the years in the year 2000s, which there are large gaps in the global coverage of data sampling, and particularly in the Southern Ocean, and the instrumentation was mostly related to shipboard measurements. So this has shown, and there were amount of several studies which have been performed, and the most recent one showing that for, in particular, the way how you map your data makes the largest difference between the different methods of estimates for global ocean heat content for the historical measurements. But there are also other differences, including, for example, bias correction for one specific instrument, which made up the majority of the measurements. So. So I just want to go back, and there's one group which is actually looking at those questions, in particular with a focus on this historical database. Then we have the improvement of the observing system through the implementation of the global Argo observing system, which had been started in 2000, and the year at about the year 2005 there was a more or less global or near global coverage of ocean heat of temperature measurements between the 60 source and 60 nose area of the global ocean. So this has been leaded to some estimates, for example my own one, and this is a comparison showing different estimates from the different groups, which are based more or less on the same data set, showing that there also still we have an enormous increase in precision in estimating the global ocean heat content, but still there are still difference between those estimates, which are ranging between values of 0.2 to 0.7. And so even this is another example, even if you just update, so the first one was the decadal trend estimate from 2006 to 2012. And if you just do a 2-year update, you can see that there is a large shift in energy storage between these 2 years just by changing the frame of the time series. So this shift in energy has been also now complemented in the discussion for the Earth's energy imbalance. And we can clearly see that it seems to have that we are coming up in a regime where there is increased heat storage. But it's still under discussion whether this is something related to the data coverage or sampling, or what are these mechanisms behind. In the lower panel, you can see that there's a comparison or implementing the method of the direct measurement at the top of the atmosphere from satellite data, together with the ocean heat content estimator, done here for different groups, and also from an ocean reanalysis. And you can clearly see that we, in particular, if we're getting more and more global in the sampling, to get a closure of the budget constraint between those two different independent methods for the Earth energy imbalance. So still, Argo is great, in particular for ocean heat content, but it's still just covering only half of the global ocean, so there are large important gaps. I do not have time to go into detail what studies has been done behind and what does it mean that we do not have any measurements, for example, in the deep ocean or in the polar regions or in the marginal seas, but they have impacts on the estimate for global ocean heat content. Finally, I didn't want you to leave out here with the view that there are just big discrepancies. This is a new study which has been done by the use of combining, it's not a reanalysis, but they have used to do the mapping by using information from the model and to fill up their data gaps. And they give a new look at the ocean heat content and the related Earth energy imbalance changes, and showing that those have been giving greater importance than previously possible. In particular, you can clearly see, as seen before, that we are in the time where we have this historical measurement, that there we have still a very huge amount of error and uncertainty. But as time is going on, we're getting closer, and in particular can be comparable to what we get from the independent budget constraint So what is this about? So why we further need to understand ocean heat content changes at global scale? So the application is, this is what has been summarized up also in our study, why we think it's the most important measure where we can see the changes in terms of the accumulation of energy in the climate system. And these are the symptoms, what is happening if there's more energy in the system than it should be. So for example, there's increase in ocean heat content, as we have seen, is directly related. Then you have an increase in atmospheric temperature, atmospheric moisture, in the global surface temperature. It's a symptom as well, and in other, but also in the global mean sea level as part of the steric one and the mass component. And so I will go over to Angélique.
Okay, so I'm going to try to give you some ideas about the observed climate variability of sea level, or at least on the variability of sea level from interannual to interdecadal timescales. So first, let me define what is sea level. So sea level is defined as the level of the sea at the surface from a reference level. This reference level can be different reference level. It can be a reference level that is an ellipsoid that is the closest to the geoid. In this case, it's fixed with respect to the center of mass of the Earth. And in that case, we are speaking about absolute sea level. And this is what is measured by satellite altimetry. And then the reference level can be attached to the ground, where we are all living. And in this case, we are talking about relative sea level, because the ground itself is experiencing vertical land movement. And this is what is measured by altimetry. Tide gauges. Now, sea level, measured by altimetry or tide gauges, is influenced by most ocean processes, but also by the transfer of mass of water or land ice from the land to the ocean. So now if you were to look at the sea level from space, this is what you would get mostly. You would see very large variations, but a static field, non-involving field with time, and you would see very large bumps and throw of amplitudes of several tens of meters. And this is mostly the geoid. Here it's mostly dominated by the geoid, which is the gravity. Then if you remove this geoid from the signal, this is what you get. You see that the amplitude of the variations are much smaller, from -2 to +2 meters. And this is a rather static field that is dominated by the mean dynamic topography. And this mean dynamic topography, basically, it's the change in sea level that is induced by the mean geostrophic circulation. So you can see the main gyres and the circulation in the Southern Ocean. But the mean dynamic topography is static itself. Now, if you remove this field again, you get the sea level anomalies. And sea level anomalies, if you look at the amplitude, it's much smaller, tens of centimeters now, compared to the 10 of meters from the geoid. And this field is dynamic, it's time evolving. And it's mostly, dominated by mesoscale features and the response of the sea level to climate modes of variability, such as ENSO, as we can see here in the Pacific, tropical Pacific Ocean. And when we are looking at the evolution of the sea level variability at interannual to interdecadal timescale, we are focusing on this small signal, actually. So now how do you measure the contemporary sea level variability? We've got two means, the tide gauges and the satellite altimetry. The tide gauges, you've got a representation of their location for the long records that are covering periods of more than 40 years. And you can see that it's biased toward the northern hemisphere. It's at the coast of the continents or on islands. So you don't get a global cover with the tide gauges. But you can go back in time up to 1850. We've got very long time series for some tide gauges, such as the one that are represented here. And you see that there are spatial variations among them. Now, although the tide gauges have a sparse cover, you can combine them together with information that is provided by satellite altimetry. So you take the AOFs of the sea level from satellite altimetry or from models, or you can do some kind of Kalman smoothing or stuff like that, and you combine them all, and you get an idea of the global mean sea level. and the global mean sea level rise over the 20th century. And this is what you get with different estimates. And you can see that there are some discrepancies among them, especially at internal timescale, but mostly they agree on the sea level rise, on its rate, and they give an idea of a rise of 1.8 millimeter per year over the last century. This might not seem to be a lot, but if you compare to what was the rate of sea level over the past 2 millennia, 2,000 of years, it never exceeded 0.5 millimeter per year before the 20th century. So this is high rates compared to the past millenniums. Now, since 1993, we've got satellite altimetry that provide quasi-global coverage of the sea level. So this is, on the bottom, you've got the global coverage of Topex, Poseidon, JSON 1, JSON 2, JSON 3 on a 10-day window. So it's almost global. And if you superimposed on the previous plot the global mean sea level that you've got from altimetry, you see that you've got a pretty good agreement. It depends also on the reference you are taking for the anomalies, but the agreement is pretty good. Now, if you focus on this period, since 1993, you see that you've got a quite steady sea level rise over that period with a trend of 3.4 millimeter per year. And you can see small deviations at internal timescales that are due to mostly to El Niño and La Niña events. And the changes in water they are inducing between the repartition of water between land and the ocean, the changes in the precipitation patterns. And it has a global signature on the mass of the ocean, and so you can see it in the global mean sea level. So now the great value of satellite altimetry is that it provides a global coverage, and you can have an idea now of the regional sea level variability since 1993. And this is the trends that you get compared to the 3.4 millimeter per year that you've got on the global mean. And you see very large variations with the sea level rise going up to more than 10 millimeter per year in the tropical Western Pacific, and to some regions that it's almost negative. So now if we try to explain those patterns of sea level trend, regional patterns of sea level trend, we remove the global mean sea level rise from the map, and we compare the sea level trend on top to the trend induced by the steric sea level, which is the change in sea level due to changes in temperature and salinity. So it's directly related to the ocean heat content that Karina was talking about. And if you compare them to, the spatial patterns are matching very well. So the regional patterns of sea level are mostly due to the redistribution of heat within the ocean. Now, if we want to go closer to the coast, because that's also very important, of course, for socioeconomic matters, because we are a lot of people are living at the coast, and that's where the impacts of sea level are. Well, we cannot directly use the past standard altimetric missions that do not provide reliable data in the last 10 kilometers of the coast. And if you go even closer to the coast, then you've got other processes that contribute to sea level variability on different timescales and that are not included directly in altimetric sea level. So you've got the tides that are removed from altimetric data. We've got the dynamic atmospheric forcing, so with the wind setup that pushes mass of water towards the coast, for instance, and the atmospheric pressure with the inverter barometer effect. And then you've got the waves. The waves, you've got the wind waves that are generated locally by the local winds, and the swells that are generated remotely. And when those waves break, the transfer of energy during their breaking induces an elevation of sea level that we call the setup. And when they break, they can run to the beach, and this is what we call the run-up. So in a case study for Cotonou in Africa, we wanted to see the relative contribution of all those processes to sea level variations on different timescales. So we selected this location because it's highly sensitive to sea level. It experiences very high erosion, and it's located in a place that experiences large swells and wind waves as well. It's in the open ocean, directly exposed to waves. So now if we focus on that, and I won't go into details, but if you want to ask me questions, I would be happy to answer them. You can estimate the different contributions from all the processes I've been talking about, from parameterizations for the waves, altimetric sea level, using the geophysical corrections that are applied to altimetry to get the dynamic atmospheric forcing. You get the tidal sea level from a tidal model. You sum them all, and you get, at the bottom, the total sea level. You can filter all the signals to get the seasonal variation, the interannual one, and the trend. And then from that, you can estimate the relative contribution of all those processes to the sea level variability, depending on the timescales. And this is what is shown here with the percentage of explained variance by the different processes. And you see that the relative contributions of all those processes greatly depend on the timescales you are interested in. So if you go to very high frequencies, of course, the tides are dominant. They explain most of the signal. This is what we see in gray. But the swells as well explain 30% of the signal almost. But if you go to lower frequencies, and especially for the trend, it's completely dominated by what you've got in altimetric sea level that represents also the climate change with the thermal expansion of the ocean and the changes in mass due to the transfer of water from land to the ocean. Now focusing on the sea level extremes, because that's where the impacts are the highest. So you take the quantile 98 of your time series, and you get the extremes, and you get the contribution as well of those different processes. And you can see them binned per year and per season, per month for the annual cycle. You see a large interannual variability in the occurrence of extremes and on the relative contribution. But interestingly, what you see in the interannual variability is that altimetric sea level doesn't contribute a lot to the extremes, but it's the only component that has a significant trend with time. So they are aggravating the sea level extremes. And now you see also a nice annual cycle in the extremes with more events in boreal winter. And this is due to the swells, basically, because the winds are higher in the Southern Ocean. They are inducing more energetic swells that are coming to Cotonou and induce more extremes. Now if we focus on one particular extreme event that occurred in August 1995, and it was documented in the city of Lagos, close to Cotonou, as the most damaging event in a 10-year period. We focus on this event, and we look at the time series, so zooming in time from this to here for a three-month window, and here for the month of August. And we plot what we have in the tide gauges in red, the tides in green, the sum of all the contributions, but excluding the wave components in black, and the sum of all contributions, but including the wave components in blue. You see that it's only when you account for the waves component that you get the extreme. It's absent from the tide gauge, because the tide gauge can't record the processes due to waves, because most of the time they are located in sheltered areas, such as harbor, and they cannot register the setup due to waves, and they cannot register the run-up, which is an oscillation anyway from this setup. So using tide gauges to study sea level extremes, it might be not the best tool to do that. So just to conclude, maybe we've seen that sea level has been rising at a rate that is quite unprecedented, and with faster sea level rise in the altimetric period compared to the 20th century. We see that we've got different processes contributing to the regional variations of sea level, from regional time scales to the local ones. And this implies that it's important to understand all those processes, to better monitor them as well, to improve altimetry in the coastal zone, which is ongoing. There are big efforts to improve altimetry in the coastal zone, so that we can get also a better understanding of the extreme events and on the relative contributions of all those processes, because you don't adapt yourself the same way to waves or to a global mean sea level rise. And I stop with that.